Um, Hi, we're Team 11. My name is Peter Grigas.
I'm Isaac Enriquez.
I'm Eden Ochoa.
And I'm Logan West.
And this is our final presentation for EXO wind turbines. So our project description. The objective of this project is to work effectively in a group effort to construct a vertical and horizontal wind turbine and achieve the maximum efficiency possible. Through the duration of this project, data should be collected through testing to successfully make the necessary calculations and reasonings for loss of efficiency.
For the design and development process of our vertical axis wind turbine, we originally designed a model that used 4-inch in diameter plumbing PVC that was connected to a laser cut piece of acrylic to match that of our model design. We used this as a prototype, as a basic proof of concept that allowed for fast prototyping, and the design was directly attached to the shaft with little contact area that resulted in some complications later on. Our final iteration of the design used the 3D printing method, where we implemented the use of a larger shaft that would be made with the process of lathing.
For the design and development for the horizontal wind turbine, our team decided to use a 3-blade design that was based on the recommendations of the NREL website. Based on our needs and criteria for the project and the scope of this class, it was appropriate. We also utilized the NREL website to gather airfoil coordinates, the NRELS 812, 813, and 814. Because the coordinates of these geometries were so tight, our team decided that the most appropriate manufacturing would be SLA printing. And you can see the results on the right, which would be on the gray. The housing, because the tolerances were a lot more reasonable, our team decided that the most reasonable thing to do was FDM printing. The housing houses many different components that assembles into the horizontal wind turbine, one of them being the lathe shaft. This lathe shaft is very special because it connects the generator to the nose cone that connects our wings. The shaft was laid and then it was milled and tapped to accept 2 set screws that would screw onto the shaft and tighten the shaft of the generator to avoid slipping when our design is producing voltage. The housing also houses a ball bearing that lightens the load of our the forces that our design will experience when we introduce our wind.
And here you can see our final design. Our main frame is made out of PVC pipe, including 1 1/4 couplings. This PVC pipes allows for extra elasticity to absorb extra vibrations caused by unaccounted imbalances. On the top, you'll see our vertical turbine, and on the bottom, our horizontal turbine. The vertical turbine also showcases that lathed motor shaft and the 12-volt motor, along with the wires in the back to be used by the multimeter for testing.
For testing and validations, one of the most important aspects of our project was selecting our wind source. Our team decided, based on our design criteria, that a 120-volt, 22-inch shop fan would be acceptable for our project. One of the conveniences of this shop fan is that it had 3 different wind speeds, and our team decided to utilize the highest speed for our testing. One of the other conveniences was that this shop fan was portable, and wind speeds was collected of all 3 different wind speeds before utilizing it for our design using an anemometer. A shroud was fabricated to increase the wind speeds and consistencies. One of the biggest challenges our group was facing was getting a consistent MDOT, our mass flow rate. If we utilized the horizontal or the vertical design and placed it just 2 inches to the right or 2 inches to the left of our previous testing position, our MDOT would change dramatically from this shop fan. This shroud reduced the 22-inch diameter shop fan to a reasonable 6 to 7 inch opening on the other end. Unfortunately, the shroud reduced the speed, even in the highest setting, by a magnitude of 350%. The wind speed was consistently getting worse using the shroud than using the fan by itself. So because of this, our team decided to be extra careful on where we're positioning our horizontal and wind turbine. We decided that the perfect distance or optimal distance would be 1/3 out of the distance from the outer diameter of the shop fan and 6 inches away from the fan. So for the testing and validation for a horizontal wind turbine, our team had a little bit of issues with our initial design. One of them being that the shaft of the generator was not concentric with the lathe shaft. We found that the biggest contributor to this issue was the set screws on either side of our lathe shaft. If one of them was tightened too much or not as much as the other, it would lean the shaft one way or the other, creating a higher force or surface area between the contact of the inner diameter of the ball bearing. And this created unnecessary friction that reduced our voltage, reduced our current, and our efficiency values. So by doing the proper due diligence and assembling our project more carefully, our team was able to get a lot more consistent and better efficiency values throughout the project. One of the other issues we had in the horizontal wind turbine was that the generator of our initial design was too large for the torque that our design was producing and would not spin even on the highest velocity of our shop fan. So to overcome this issue, our team switched over to a smaller 5-volt DC generator from an Arduino kit. We just needed to update our SolidWorks file and FDM print our new housing to accept this generator. Next slide, please. For the testing and validation for the vertical turbine, the original vertical turbine consisted of a PVC / acrylic assembly. Because of this assembly caused a lot of vibrations in our project, and the imbalances is one of the reasons why we were getting small efficiency values. We decided that one of the biggest contributors to this issue was that the generator shaft was too small to directly attach to the turbine profile. To overcome this, our team created a shaft using a lathe that would connect the turbine profile to the shaft of the generator and increase the surface area on both ends. And this would significantly reduce the vibrations and give us more consistent readings for our voltage output and efficiency values. One of the other things we did differently for the vertical turbine was to replace the PVC acrylic model to a 100% 3D printed turbine. And this meant that our final product was lighter. It was, and also gave us more consistent readings with the geometry given from our FDM print. Next slide, please.
For both our vertical and horizontal design, in order to calculate the efficiencies of the turbines from collected data, we use the equations below. For the vertical design, we calculated our flow out from a multimeter data collection, collecting the voltage and current, calculating the power. And then for the flow in, we used Bert's law to calculate the maximum possible power. For the horizontal, we used the same method for the flow out, and then for the flow in, we used 1/2 mass flow rate velocity squared for the maximum possible power. And then for both calculations, we assumed that the mass flow rate entering and exiting the system was the same. Next slide, please. So for the horizontal turbine, we tested on various occasions, and our most consistent and consecutive data set was shown in the table below. We collected the voltage, the current, the airspeed going into and out of the system, collecting an average efficiency of 4.65 for the horizontal turbine. For the vertical turbine, we did the same, collecting voltage, current, and then the airspeed entering and exiting, collecting a average efficiency of 4.98 for the vertical turbine.
Some justification and reasoning for the loss of efficiency in our project is due to mechanical energy being converted to thermal energy through the process of friction heating. We also lost some efficiency because of the slight errors in the manufacturing process of 3D printing and lathing the shafts of our design, which resulted in unequal balances. And then we also experienced little fluctuation in speed with the wind, creating changes in our results. In conclusion, the data we collected and the results we experienced were not surprising due to the design factors for the wind turbines, the use of no air shroud, and the differences in the wind source. The average efficiencies for our vertical turbine was 4.98% and the horizontal being 4.65%. The team objectives were met and the efficiencies losses have been investigated and understood, and our team is pleased with the results and the overall completion with our design. And then these are our references where we earlier described that we reference the design of the profile for the horizontal design for the airfoils. And then for our Savonius wind turbine for the vertical design, we used the Betz equation and some other information regarding that topic. Thank you.